So this picture is exactly the same as the previous one. Okay, so we already know that we're going to have a force going this way and a force going this way, right? And when I break that into perpendicular and parallel components, it's almost parallel, but just a little bit of perpendicular. Okay, so here's F parallel, here's F perpendicular, this is FB. So, okay, so yeah, my drawing is getting a little small here, but I've got this parallel and this perpendicular component over here, and then on this side, I've got a parallel and a perpendicular component. Okay, so F parallel, F perpendicular. And so we see that we have a torque on this thing that's going to make it turn counterclockwise. Okay. And if it gets horizontal, which it will pretty soon, right? If it's going this way, if it's going counterclockwise, it doesn't have very far to go before it's horizontal. And then the torque goes away, as we saw in part D of the previous one. So this one is going to head for a equilibrium position that's not far away. Okay, how about this one? So now I've reversed the directions of these currents. So that means I've also reversed the directions of the magnetic force. So now they're going to point like this. Okay, and so I've got a parallel and a perpendicular, and I've got a parallel and a perpendicular. And so this is going to cause a torque, and it's going to cause a torque that this time is clockwise. So in this case, this loop is going to move away from the equilibrium position. And it's not going to reach equilibrium again until it comes all the way horizontal, going this direction. Okay, so and effectively, this loop is going to flip upside down. So this is the unstable one. It's going to take a longer path back to equilibrium. This is the stable one. Okay, any questions about that? Okay, last one. We're going to use the work energy principle on this one. We know that if we do work on a system, that will change the total energy of the system. You guys remember the work energy principle from last semester? So the work that I put in is going to equal to the change in the kinetic energy plus the change in the potential energy of the system. In this case, our bar magnet starts at rest and then ends at rest, so there is no change in kinetic energy. So effectively, I just need to know what's the change in potential energy, and that tells me how much work I have to do in order to create that change, in order to put that much energy into the system. Okay, so how do I figure this out? Well, delta U is going to be U final minus U initial. Well, what is U initial? So it's equal to the negative of mu dot B, where mu is the magnetic dipole moment. That's this guy. That's mu. And the magnetic field for Tesla, that's B. Okay. Now I can calculate the dot product by using the magnitudes. So it's going to be the negative magnitude of mu times the magnitude of B times the cosine of the angle between them. So mu and B are not changing, but theta is. So I'm going to call this theta initial. And what is theta initial? It's the angle between mu and B at the beginning. Well, it tells us that the magnetic dipole moment is aligned with the magnetic field to start with. Okay. So that means theta initial is 0. They're parallel, which means that U initial Cosine of 0 is 1. U initial is negative mu b, where these are magnitudes now. U final is going to be minus mu b cosine theta final. And what's theta final? It's telling us that now it's pointing the opposite direction at 180 degrees from the magnetic field. So theta final is 180 degrees. Cosine of 180 is negative 1. So that's going to cancel this negative. And so I get mu b. All right. And then lastly, I can figure out W, which is delta U, which is U final minus U initial, which is mu B, that's my U final, minus negative mu B, that's my initial, minus a negative. So I've added mu B to mu B. 2 mu B is the work that I had to do. And now you can plug in the numbers. I like to always do that last. So it's going to be 2 times 15 times 4. So that's 60 times 2, 120 joules. Any questions?